So evening again, everyone. So in this session, we are going to see how to build a mobile robot from scratch and integrate the proximity sensors and program it in such a way that it avoids the obstacles in the environment. So I might have shared a folder with you, or the coordinators might have shared a folder with you, and that folder mainly consists of three files. The first one is the setup of the Copilot sim, in just in case if you have not if you could not able to download it from the website. So this is a Windows supported exe file, and this second one is the environment of the robot that I will be explaining it in few minutes time. The third one is the hands-on procedure that basically tells the dimensions and other parameters for the robot that you need to feed to the software in the duration of this training session. Throughout the duration of this training session. All right, so make sure you enter the right values during the training in the software wherever required. If you miss something here, nothing will happen, but your robot might not work in the most accurate way, but that's all right, not a problem. This environment without robot, this file is something like this, where I'll be sharing an environment something like this to you. It contains an environment something like this. We'll be building a new robot in the new scene. Then you can create a new scene by going to file and clicking the new scene. You can create a new scene, and you can close it by going to file again and close scene. All right, and now yeah, so it will be something like this. All right, so after creating a new robot, you need to copy it and paste it in your environment without robots, and then it will become something like this. All right, so then when you start the simulation, this will happen. Right. All right, so it needs to traverse in the environment by avoiding the obstacles. All right, it needs to traverse throughout the maze. All right, by avoiding the obstacles. So so the sensors has to sense the obstacles and send the feedback to the robot in such a way that the robot has been programmed already, so that also will be doing it in a short while, and avoids the obstacles and traverse within the maze. All right, so I'll stop the simulation for now, for time being, and we'll go to a new scene and we'll start creating the robot. Yes, so I'll be following the values that I gave you in the you might be having you'll be having the PDF version of this file. So I'll be following the whatever the values is there, so I request all of you to follow the same. So now we'll go to so basically, as I already mentioned in the other session, so this software has many robots, right? Non-mobile robots, mobile robots also. But building a mobile robot from the scratch and programming it would give you more exposure to this software and gives you more confidence that no, you could able to do as if that you I like you basically you know a lot of things. Then like using an existing software, if you create your own robot and programming it and integrating the sensors to it, it will you'll get to know like more options within the software. All right, so now we'll start with the building the body of the robot. All right, so go to add, go to primitive shapes, and go to cuboid. Select cuboid. So the dimensions that I now gave are as per the file that I have shared with you. It is 0.2 in x, 0.2 in y, and 0.1 in z. All right, okay, So now one important thing is that don't try to move the object in the environment. So once it is created, it should not move, right? It should not be moved to the other places. Then you might find an error when when adding wheels to it. So it will not be in the right place, right? So we have created a body now. So the second step is you have to translate in the z direction slightly upwards. So you can see a coordinate frame here, the reference frame here. So when you move the environment, even the reference when you reorient the environment, the reference frame will also be reoriented. So we need to move the body of the robot in z axis so that the body will not uh, there won't be any friction between there won't be any contact between the body and the floor. So we are moving it in the z direction. So select the body, and in the z direction just translate it little. Yes, so it is now translated. So now you can see a small gap between, right, the floor and the, yes. So now position. All right, cool. So now so select the object and go to tools, scene object properties. So we need to change some dynamic properties now. I'll tell you what we are going to change. So now go to the dynamic properties. So now go to scene object. First we went to the scene object properties. From there click the dynamic properties dialog. So make sure the body is respondable, make sure the body is respondable and it is dynamic. If it is not dynamic, the body cannot move. If it is if it is not respondable, it cannot hit the other objects, right? There won't be a collision between the other objects. It just passes through the other objects, right? You can try with these options by changing this option in your leisure, but for now just make sure the both these options are checked in. And then after that go to the common properties and make sure these special object properties are all checked in: collidable, measurable and detectable. All right, so now close this and rename the object as u qbot. See? Cuboid robot, qbot. All right, so now we have mm, built a body of the robot. Now we'll add a sensor and integrate it to the and assemble it to the robot. All right, just go to add proximity sensor, randomized. You can choose whatever the type you want, but I'll always go with randomized retype. So something like this will come. All right, so now we need to rotate it in such a way that it is aligned with the front side of the vehicle. All right, of the robot. So now choose the rotation and go to the rotation and just give 90° in y and z direction. All right, 90 degrees in y, 90 degrees in z. All right, so now give rotate selection. So it will be, now the sensor is facing the front side of the robot. All right, so now choose this option of shift. So basically you can like move it in the linear direction. So now position, go to the position and choose 0.15 in x, 0.15 in x, and in z 0.05 in z. All right, close this and finally go to the tools, scene object properties, and go to the volume parameters and choose the offset as 0.005 and range is 0.05 and the angle, sorry, 0.15, and the angle is 30 degrees, sorry, 30 degrees. All right, fine, close. So now we have built the body of the robot, and now we have built we have like added a sensor to it, but we did not assemble it. All right, so now the final thing is that okay, before that, just select the sensor, go to tools, scene object properties. All right, show detection parameters, and make sure that this last option is checked out. It should not be checked in, it is checked out. Don't allow the detections if the distance is smaller than, so this option needs to be checked out. So I'll explain the reasons. If you have any questions with this, I'll explain it during the the question and answer session, why these options are checked out and checked in and all those things. I'll explain it later. And just give OK, and close this. Now we can rename it as uh, qbot nose, or just nose. Just nose is fine, right? So that when you are programming, it will be easy for you. Nose. And the final thing is that you need to assemble it to the body of the robot. Otherwise when your robot moves, your sensor won't be moving with the robot. It will stay in the same position. All right, so you need to assemble it. For assembling the sensor to the robot, first you need to select the nose first, and select the body and assemble. All right, so first the object that you are going to assemble needs to be selected, and the second selection is the object to which that you are going to assemble. So select that as secondly, and just give this assemble option. It will be assembled. Otherwise, simply just drag the object that you want to assemble to the object that you need to be assembled to. Just put it there, it will be assembled. All right, that would be easy for you. So now we have got the sensor. Now we have to model the wheels. For modeling the wheels, just create a new scene. I like in a short while you get to know why we are going for a new scene. So add primitive shape, and select a cylinder, and the dimensions are as per the dimension that I gave you. It's 0.08 in x and y, and in z it is 0.02, and just give OK. That's it. So we got a wheel that is in the fallen position. So just go there, just go to this option, and go to position, so now go to position. It is 0.3, 0.2, and 0.1, right? So now we have changed the position, and select the wheel and go to the tools, scene object properties, and make sure in the dynamic properties, make sure the body is dynamic and respondable. All right, and go to the common properties now, and make sure the objects are collidable, measurable, and detectable. All right, and close this. Now we need to change the orientation of the wheel. Now it is in the fallen, it looks like as if it is fallen from somewhere, and we need to change its orientation. So to make it stand, so go to the select uh, this option, object item rotate, and go to the orientation, and just give uh, -90 in the alpha, right? -90 in the alpha, right? So that you can see the object is standing. Fine. So now what you have to do is just copy it, and copy is Control C, and paste it 3 times, 1 2 and 3. So you can see in the tree scene hierarchy, you can see the three 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 objects are now copied and pasted and renamed. The all 4 objects are renamed accordingly. So now we need to give the positions. Now we'll rename everything. All right. So we'll rename it as left front, capital, left back, let's go, wheel, and left front, wheel, right back, wheel, so like we are creating 4 wheels and we have renamed them. So and now just select the left back wheel, and go to the this object item shift, and go to the position and change its position to and again all these positions are there in the file, PDF file that I gave you, -0.1, 0.13, and 0.04. all right, fine. And now select the left front wheel, and now the positions are 0.1, 0.13, and 0.04. Right. Now select the right back wheel, -0.1, 0.1, minus 0.13, 0.04. all right, and in the same way the fourth wheel is -0.1, -0.13, 0.04. right? Sorry, this plus 0.1, sorry. all right, fine. Now close this, and the final step with the wheels is copy all 4 wheels. Just copy and then go to the this other scene and paste. So now you can see so all the 4 wheels are neatly placed on the 4 sides of the body. all right, so that is why I told that the values that I gave you are really important. If you miss any one value among all the values, if you made a mistake in any one of the values, your positions might change. All right, then you have to like do it again or check all the positions. all right, so now we have built a body, and we have integrated the sensor with the body, and we have built 4 wheels. Now again we need to integrate motors to the wheels and assemble it to the body. all right, so fine. Now go to add joints, select a revolute joint. So revolute joint is basically rotary joint. You know Basically we use it's a motor. In other terms, it's a motor. All right, revolute joints. So now select select the left back wheel and select the revolute joint. Go to this option, object item shift, and sorry, so select the revolute joint and select the left back wheel. So now what you have to do is you need to your wheel, your joint, as you can see, is present in the middle position, right, in this position. So now you have to like move it to one of the wheels. So I choose left back wheel. So you need to copy the positions of the left back wheel and apply it to the your revolute joint, isn't it? So now what we did is first select the revolute joint and select the left back wheel, and select this object item shift and go to the position tab and give apply to selection. All right, so now you can see your joint has been uh, your position of the joint and the position of the wheels are now same and they are aligned. And only thing that that we need to do is to change the orientation of the joint. So for that, you know uh, your guess might be right. You go to the object item rotate and go to this orientation tab and apply the orientation. All right, and that's it. So now you can see your joint is neatly aligned with the wheel. Fine. So now rename the joint as left back motor, left back screw motor, right? So now assemble and now go to the tools, select the motor. Now go to scene object properties and go to the dynamic properties and turn on the velocity control mode. All right, so we need to control this motor by controlling the velocity, right? You have different options. If you want to try, you can do it at your leisure, but in this exercise we are going to control the velocity of the joints, all four joints, in order to move the robot. All right, so just give the target velocity as 0, because if you keep it if you give some value here, when you start the simulation, the robot immediately starts moving even before your program gives the control target velocity, right? So for that reason we are keeping it as 0, and that's it. Engine properties are nothing. Yeah, just close this now. All right, so, and rename this. We already renamed it, and assemble it to the motor. Assemble the wheel, left back wheel, to the motor. All right, and assemble the motor to the keyboard. All right, so now you can see the tree, the hierarchy. So I forgot to explain to you about the hierarchy, I guess. So the hierarchy is whatever the objects that you add in this, either it could be a sensor, robot, or motor, whatever joints that you add in this uh, in the environment, that will be comes to the hierarchy. It will be displayed in the hierarchy. You can see it here, like what is the position of this, which to which object it has been assembled to, and everything. It will be in the form of tree. All right, so it's an important aspect of this Copelia sim. Fine. So now we have assembled the sensor to the body of the robot, and we have assembled the wheel to the motor, and the motor with the wheel to the body of the robot. Fine. So we have to like repeat this step. So that is create 3 more motors. All right, create 3 more motors and assemble them to the wheel, respective wheels, and assemble them to the Qbot. All right, so what I'm going to do now is I'm just skipping the other adding other motors, and I'll let you to do by yourself. If you have any doubts, you can ask me during the session. Fine. So all right, now so now the next step is copy copy the whole robot. You have to copy all the components, right? You cannot copy only the body and paste it there. Just Control C for copy, and go to this environment and paste it there. All right. So now so we have copied and pasted our robot in this environment. So now our final not the final step, now the next step is to um do the programming, right? So now just right click in this right click the body of the mm, robot, and go to add, and add associated child script, and go to non-threaded. All right, and select Lua. So in the previous versions of the Copedia sim, that there was no options for Python available, right? So only in this current version, which I guess it was released like last month, a couple of months back, they have included Python as a programming language. If you are familiar with Python, like you can explore it by yourself, but I never used Python within Copelia sim, so I just don't want to take a risk at the last minute. So I just decided to go with the Lua script. But anyways, like if you want to try Python within the script, you can do it, but not now. You can do it in your leisure. Just double click the script. So once you have added the script, there is a document icon that has been added beside the qbot body of the robot qbot. So just double click on that icon, so your script will open. So the basic script structure, it's a functional. Lua is basically a functional programming kind of a script. So where you'll be having four functions, you have to do all your coding within those functions, right? So fine. So the first function is to initialize your variables or parameters, and the second function is mainly for the actuation, and the third function is for sensing. So if you want to like sense something, for example in this case want to sense the obstacles, and you want to like plot it in a graph that I have I have shown in the beginning of this session. So something like that, if you want to do, you could use this function. If you want to actuation in the sense, like obviously we are like actuate the joints or motors that we have created to move the robot, right? So those coding will becomes under this function. And system cleanup is once you execute the cleanup function, like what you want to do, like when you're closing or something like that, the cleanup function. Fine. So what I'm going to do now is, so I have copied the program here. I've already did the programming and copied them here. So like typing would take more time, right? So what I'm going to do is I'll just copy all this coding program step by step, and I'll explain it to you. All right, step by step I'll copy and paste. Instead of typing, I'm just going to take copy it and paste there step by step. So fine, I'll copy all the variables that I'm defining now. Fine. So yes, so I'm leaving this alone. I'm going to leave whatever. So yeah, so these red scripts I'm going to leave for now. Once our actuation program is action function is validated, then we'll go for the sensing part, the graph part. Fine. So now I'm just going to define all the variables, like initialize all the variables in this initialization function. So let's just paste it. Fine. So before that, and one final step is oh yeah, this graph is also not needed for now. We'll add it later. Yeah, cool. So what we did is so we have created different objects such as body of the robot, sensor, and motors, wheels, and everything, and we have integrated, assembled them to the body of the robot, and everything is done. So if you need to, like, for controlling the robot, you need to control individual motors, right? Like you cannot like control the whole robot. You have to control the robot by controlling the motors. That's the concept, right? Basic concept. So hence we are calling all four motors, initializing all four motors to the function, and we are like defining this qbot base here. Why? Because this is where we have created the script, right? This is the reference point. So this is where we have created the script. That's why we have given dot here. So this is the our reference point. From this point, where is your left motor? From this point, and your left back motor, the variable left back motor, this left back motor here has been assembled to your qbot, right? So by keeping this as a reference, dot as a reference, and you are calling the left back, the name called left back motor. So basically sim dot get object is the command for the Copilot sim. So for calling an object that you have created, and that is available within the hierarchy, scene hierarchy of the tree. If you want to call and get the object and get the values that the object is publishing, or if you want to control that particular object, you have to use this command called sim.getObject. So using that command, within the bracket, you need to call the name of the particular object, right? Name or location even. Your origin is dot. Dot is where you have created a script. The location of the script that has been that is located in the this associated with the base. So from base, there is an object that has been assembled to the base called left back motor. So I am mapping that particular object to the variable name called left back motor in the script. Fine. So by this way, I'm calling all four motors, and the nose, an object called nose, I'm mapping that with the name called sensor. Fine. So now it is done. One like for your information, so there is an API website. There is in the Copilot Sim Robotics, in the Copilot Sim website, Copilot Robotics website. So we have APIs. So for example, if you go to Google, APIs. So yeah, API references. So if you go there, so you have all the commands that are there. So you can like select, for example, the sim.get object, right? Get objects, get object. Yeah. So this is the command, first command that we have used till now. So the details of all the details of this particular command will be available here. You have to go to this page, and you have to, currently we are using a Lua programming. So this is the syntax of that particular command, how we have to use it, and like what are the variables that you have to give feed as an input, and those things, and the explanations, everything will be there. Suppose if you are using Python, your reference will be here. All right, C, C++, etc. Right. So now we have initialized all four motors and the sensor. Fine. So now we have to do the actuation part. So before that, I'm just adding these two commands. I'll explain it now. Fine. So speed is nothing but like how much speed that you want your robot to move, right? You could able to. I'm just roughly that there is no reason why I kept 100. I just kept 100, so that it feels like a decent speed. That's why I kept 100 back until 10. So I'll explain what is back until 10 and shortly. Fine. Fine. Next is actuation. For actuation, I'm just copying all the commands now for now. Right. Cool. So now under the parameter variable called result, so using the command sim.read proximity sensor, I'm just reading a sensor. What is sensor? Sensor is the variable that has been mapped with the actual proximity sensor, right? So under the variable name called result, I'm reading the the readings of the sensor. Fine. So in this this I'm using an if function here, just checking if the result is greater than 0. So read property, if there is an obstacle, the result will be 1, right? And if there is no obstacle, if there's an obstacle, the readings won't be 0. So the readings will be a reading will be a distance, right? The distance between the obstacle and the robot. If there is no obstacle, the result will be 0. If there is an obstacle, the result is I mean, if there is an obstacle sensed by the sensor, the result is obviously greater than 0. So hence your back until time will be like your back until time variable will be updated with the current simulation time plus 4 seconds. So your sim dot get simulation time actually gets the current simulation time. So when you start running the simulation, your simulation will start incrementing from 0 to 1 seconds, 2 seconds, 3 seconds. So by this way a timer will be started running. So so when this condition reaches, it gets the current simulation time. For example, if it is the 5th second, at the 5th second of the simulation, if there is an obstacle that gets detected, your back until time will become 9. The current simulation time is 5, and we are adding 4 seconds to it, and it becomes 9, right? And if back we already know the current simulation time, that is 5 seconds, and we already know that the back until time will be greater than the current simulation time, since we are adding 4 to it. If an obstacle is detected, but your back until time will be greater than the current simulation time. If it is less than the current simulation time, then obviously there is no obstacle. So that is that you might have understood using this by like when I was explaining this before. So basically your back until time will be updated based on the presence or absence of an obstacle. So if there is an obstacle present, this logic will be these commands will be sent to the motors. If there is no obstacle, these commands will be sent to the motors. If there is no obstacles, all the motors will be running at the same speed, the same direction, so to move the robot in the same direction. If there is an obstacle detected, then your left side motors on the left side of the robot will be running in one direction, and the right motors on the right hand side of the robot will be running in the other direction, opposite direction, to turn the robot. All right, so this is the logic now. So if you have any doubts in the code, please raise anytime during this training session. So now we'll start running the robot. We'll see what happens. Now when I start running the robot, you can see the simulation has started, and the sensor senses the obstacle and it rotates, right? If it is not sensing an obstacle, it does not rotate. So the problem with having one sensor is that the robot, most of the time the robot will not go out of this segment of the maze, right? If so you can see again, if it senses an obstacle, it is going to turn to its left, right? So it is going to like be within this loop forever. So suppose see this scenario. So in this scenario, like I have two sensors attached, right? So now if you see when I start the simulation, you can see the robot depends on the side, it could able to turn on both sides. Sometimes it gets stuck like this, but sometimes it gets stuck like this. So but still but there's a chance that it will easily go out of this loop. Since it is having a two sensors, there's a good chance that it goes out of the loop. So I highly recommend you to the add another sensor the same way that we have added a nose sensor. And if you want, you could rename it as eyes. You rename it into eyes left and eye left and eye right. So and you could alter the code that we did. Do you just need to like initialize another sensor in the code? You need to initialize another sensor in the code. Sorry, I need to initialize another sensor in the code here, and you need to change the logic appropriately. So you'll be having a you have to read two sensors here, you have to initialize another sensor here, you need to add another, you need to read another sensor, and you have to change the logic accordingly. So by this way you could make the robot to turn in both the directions. All right, so now so we saw that our logic was working good, our actuation part was working good. Now we'll go for the this sensing part. Yes, sensing part in the sense we are going to add a graph here, and make the graph to show the readings of the sensor. All right, and all right, we'll change the code now. So before changing the code, we'll add a graph here. Just go to add, there'll be a graph. Okay, so add a graph. So a graph will be opened here, your tab will be opened here. Again attach the graph to the robot, so you can assemble it to the robot. So now we can call this graph to the code. Yes, so now we'll go to the code. So this is the where's this actuation port? Yes, yeah, so these two commands. All right. Yes, so in the initialization what I'm going to do is, so again similar to the previous initializations, how we have initialized our sensors and motors, same way using the sim.getObject command, we are initializing the graph where the graph is attached with the robot, its location. And we have a distance stream. We are adding in, we are initializing a distance stream that is nothing but the graph, a variable that basically used to stream the data to this graph. What data that needs to be streamed, that just to like to configure what you saw here, the graph, right? So in the distance stream, so using the command sim.add graph stream, where you want to stream, you want to stream in the graph, right? So the first option is graph, and the second option is um, what is the name that you want to be there in the legend, suppose so here, so there will be a legend, so this legend, see, keyboard clearance. So the legend, which one do you want, and obviously which color do you want to stream? You want red color, so this is the RGB format. So if you give one here in the R, you'll get red color. So if you want a blue color plot, just give one there, so I'll be automatically your this thing will be changed to blue. So if you want more details about these commands, you can, as I already mentioned, you can go to the Copiliasim website, and you can search for the APIs and look for this command or any other command you want to you want more details of, and you can search for the command and you get to know more about the details of these things. Fine. So we have now initialized the variables for the graph. So we'll stop the simulation for now. And now once initialized, we are now I'm just directly adding this function, sensing function. So I'm just adding right here. So here you can see there's a function, new function. It's a default function. When you open a new script, so this function system call sensing will be there. I'm not adding anything new. I just removed it in the beginning. Now I'm just adding it. So these are the things that I've added new, right? So again, we are reading a proximity sensor. The read proximity sensor basically gives you two outputs. The first one is the result, that's a discrete, like we saw here, that's a discrete, whether the obstacle is there or not. That's a binary output. And this one, distance left is nothing but the distance between the obstacle and the sensor. So those things. So you are basically your read proximity sensor command gives two outputs. So using this command, you are reading the sensor. Sensor is nothing but your actual sensor that you have assembled to the robot, attached to the robot. So, and again, if the result is greater than 0, means that if an obstacle is detected, only then you want your graph to be streamed. So this is not mandatory, right? So this is like just to avoid um, uh, unwanted processing. We are just using this loop that basically reduces the processing. If only the obstacle is detected, your data will be streamed. Otherwise, anyways, the value is 0, so there's no need for it to stream the 0 value. All right. So, and we have a command called sim.setGraph stream value. So this command basically streams the data. It requires three inputs. The first one is where you want to stream, and the second one is what you want to stream. So basically distance. So in what format do you want to stream? So this is the format I want to stream. And what is the data that you want to stream? This is the data I want to stream. All right. So where you want to stream? I want to stream in the graph that I have added to the robot. And which format do you want to stream? I want to stream in the format that I have defined here. And what data I want to stream? I want to stream this data, basically the reading, the sensor reading I want to stream. So now upload it and close this. If you run the simulation now, when the obstacle is detected, you would be able to see, the values are plotted here only if the obstacles are detected. All right. So now suppose I'll just show you what happens if I remove this logic here. So I'm just uploading this, and if I run, it will start from the beginning. The streaming will be start from even though if there is no obstacle, it will give us the data 0. All right. If there is an obstacle, then it will be something like this. The plot will be something like this. It is, you cannot read anything from this, right? So it's unnecessary processing. So that's why we are basically using this line. unless there is an obstacle, no data will be streamed. So now I want you to try this one. Once you are done with this, I want you to like it will be good for you if you try with adding another sensor, moving this sensor to the left end of the face of the robot, and add another sensor on the right end of the face of the robot. Sorry, face of the robot. Then just change the program accordingly. Just try it once you whatever I did, if you could able to achieve within a minimum time, and you have like good time left within this session, and you can try adding another sensor and change the logic and so on. Yes. That is all about this session, training session. And if you have any doubts, please feel free to raise the questions. And if you have any doubts in the other softwares or tools that I have handled in this session or the previous session, please feel free to raise the questions. If I couldn't answer properly, I'll get your email ID and I'll respond to you with the answer. Yeah. Thank you so much for listening.